Thank you so much for surviving all the way to the last session. We started out on our first day with so many contestants, and now on day 5 of Survivor, we have all of you left. But yeah, no, thank you so much for making it. I'm very excited today to talk to you about all the exciting things we've been finding in the first billion years as we are looking at this very unexplored epoch of the universe with JWST really for the first time. Before I started off with the science, I wanted to take a moment to acknowledge that it really takes a village to support a fellow's career, and over the last year I've been very fortunate to have all these people really help me in a variety of ways, ranging from papers to proposals, the highs and the lows, and the ups and the downs. I also wanted to give my thank you to the NHFP, the program, and its organizers by telling a bit of a story. So like I was mentioning in a session a few days ago, right? It's been a few years since I got a chance to go back and visit my family in India. It's been 4 years. And during that time, my grandfather passed away, who's pictured here. And I went and visited his small little village, in the northern part of India. And it was amazing to see that everyone there recognized me, even though it had been 10 plus years since I had gone there. And that is thanks to this very niche YouTube show that explores astronomy in Hindi and Urdu, targeted to a South Asian audience. And so this professor, Salman Hamid at Hampshire, runs this YouTube talk show, right? And the reason he found me was because of the NHFP press release last year that goes to virtually every astronomer's inboxes. And so I just wanted to acknowledge what a privilege and what a great role this fellowship program plays in astronomy in general. And to us personally, by placing us in this very special position of being ambassadors for the field. And so if not for that, I wouldn't have gotten the chance to be on the show and to be on this video where I really was able to explain so much of my research in a language that my grandfather and his friends understood. So thank you. And with that, let's dive into the first billion years as advertised and promised. So this is one of my favorite plots in all astronomy. I know it's very it's shown everywhere, but it also always blows me away that in these pixels we contain the entire history of the universe. It's from Avi from 2006 Scientific American article, back when he really cared about the great oceans of neutral hydrogen. Nowadays he cares about the great oceans here on Earth, which is also amazing. Love him. But yeah, we start out with the Big Bang, then the universe is an entire ocean of neutral hydrogen. The first stars and galaxies form, these small pinpricks of light come alive. They reionize the universe, they heat it. It's a very transformative event. And on the other side of it, today, sitting in a small galaxy like this, we are trying to figure out this grand story that has unplayed before us. So today, I want to talk to you about 3 categories of objects that have really seized mine, and I think the community's imagination over the last year when JWST first turned on, and during its first year of operations, it has shown us these new classes of objects that we did not expect. And so yeah, this will be a very breezy run through. I'll try to show you why we discovered them now, why I think they're interesting, and kind of where we're going with these things. So let's start off with something that we've already heard quite a bit about, thanks to Sultan's great talk yesterday, this discovery of very bright galaxies at extremely high redshifts, and what that means and where that field is going. So the context for this is that we've tried to push our cosmic frontier farther and farther ever since we had our first large telescopes, right? And so with the Hubble Space Telescope, we were able to peer all the way out to a redshift of about 11-ish. So this is a galaxy, GNZ11. It was discovered with the Hubble Space Telescope in 2016. I was an impressionable young undergraduate visiting Yale University as an exchange student when Pascal Ush made this discovery. And so yeah, so this was our farthest beacon in the universe in terms of starlight for several years. And you can see we really were pushing the limits of our existing instrumentation to find this object. So because of the redshifting of light, and the absorption of blue photons in the intergalactic median, these galaxies, these very distant first galaxies, are detectable only in the infrared. And so you can see that to make progress, we really need to push farther with a larger, more sensitive telescope. And that's exactly what JWST is. This is, sorry to my exoplanet peers, but this is exactly what JWST was built to do, right? And so within, within months of it being turned on, we were already seeing how easy it would be to chart these new cosmic frontiers, right? So in the first data release, just popping out, we saw this galaxy, this very robust redshift 12 galaxy candidate that's extremely well detected in these far infrared bands and completely invisible to our earlier facilities. And not only were these galaxies there, we did expect there should be galaxies out at these early times, right? Like things like in that cartoon that I was showing you, these pinpricks of light were turning on. But the real surprise, of course, was how bright these galaxies were. They were way brighter than any of our models predicted. And in some cases, they also showed signs of being very evolved. So for example, this object, Wren here and Erica Nelson helped model it to show that it is consistent with having an isophotal profile that might house a disk already at these very early times. To put it in a more statistical way, so this is a galaxy UV luminosity function, where we are basically plotting brightness on the x-axis and how frequently objects occur on the y-axis. And so what you're seeing here, right, is that no matter what you use to form your template for expectations, be it like empirical extrapolations or some kind of very pure theoretical extrapolations from, say, dark matter simulations, you see that these galaxies are way more abundant than they should be by more than a factor of 10 to 20. So an end of year one goal that needed maybe 10 times larger survey areas was already fulfilled within the first data releases itself. So what is going on? So this is something that really seized the community's imagination. There has been no dearth of solutions, but the two main points that I want to leave you with about this particular conundrum is one, that it's really solid at this point, right? So it's not just these early few galaxies, but since then, work that, for example, Seiji and Richard Bowens and many others have done have shown that this persists across all fields, across all the data we have studied till now. The second point that I want to emphasize is that despite this being something that has excited us so much, there's been shockingly little follow-up data and follow-up time that has gone into this particular problem. So for example, these two sources that I was showing you that we discovered almost 14 months ago are yet to receive spectroscopic follow-up, but that's going to happen soon. So that's going to happen next month. So stay tuned for some very exciting updates on this from these two programs. I'll show you some other solutions and touch on this problem again in the next few slides. So keep this at the back of your mind. The other thing I wanted to emphasize today, so I'll be talking about some of these baby AGN and little red dots that we're finding. But the broader point that I wanted to make was that JWST has been showing us these beautiful images at these heretofore uncharted wavelengths, but we're also for the first time really seeing the insides of galaxies at these relatively lower redshifts, redshifts 3 out, for the very first time with these rest optical emission lines that really are our workhorse tools to figure out what's inside galaxies. Are they being powered by black holes? How much star formation there is? So we're really seeing these diagnostics for the first time at these redshifts. And so in this first year on the Hubble Fellowship, I had the privilege of being involved and leading 5 programs, most of which were really focused on getting these spectra and seeing what's inside galaxies in these first billion years, something that we've wanted to do for several decades now. And in particular, I've been doing a lot of NIRCam prism spectroscopy, which is a very special and very underrated mode on the JWST telescope. So what this mode does is it basically disperses light from every object in the field of view. So you get a spectrum for everything. And this has proven remarkably successful, right? So to summarize, even though a very tiny fraction of cycle 1 time went into this mode, it is producing by far the largest spectroscopic data sets. So now we are able to talk about thousands of galaxies with spectra at these redshifts, thanks to this mode, up from 0, right? Rest frame optical spectra. And so what this has shown So here's one really exciting result from our team, where you could say that if you really have these very bright objects at super high redshifts, you should see some very massive descendants of theirs at lower redshifts, right? So where are they? And when you have these kinds of numbers, when you're talking of thousands of spectra, you're able to hone in on very rare objects. And so we were able to find galaxies that seem to have Milky Way-like masses already at redshift 5 to 6. And so we're not just saying this from photometry, right? We have spectra for all these objects. So they are at the redshifts we think they are forming stars at crazy rates. And so we see this with emission lines. The other thing that we were able to do is we were able to hone in on this very interesting class of objects called, we are calling them little red dots. I'll show you in a second why. The context for this is that for the longest time now, in the first billion years, we've known of these very bright, really spectacular quasars, supermassive black holes that are just among the most luminous objects that you see across the whole sky, right? So we're talking absolute magnitudes of -30. And so this plot summarizes the state of this quasar AGN field before JWST, where we knew of many of these bright things at these early redshifts. But what is going on at the fainter end is completely a puzzle, right? And we knew there should be like smaller black holes, right? Because these really enormous beasts didn't come out of being, according to many of our theories, out of nowhere. They should have probably aggregated from smaller seeds of various kinds. So where were the seeds and how common was their occurrence was one of the key open questions. And so indeed, in the first images that we got from JWST, we started seeing these very compact, very red objects in JWST bands everywhere we looked. So pretty much every deep field, every NIRCam deep field had one of these objects. And so when we looked at these kind of very compact sources with these GRISM spectra, we saw that essentially virtually all of them had these broad components in their Balmer lines. Couple more minutes, right? For questions plus, yeah. With Balmer lines, showing that these basically are these very broad line AGN that we know and love at lower redshifts, but we're seeing them for the first time at redshift 6+. The key thing I'll tell you about the little red dots in the faint AGN is that they basically are way more numerous than anyone expected. They're everywhere, and this is proving to be like a huge puzzle for simulators to figure out in terms of like where the seeds for these black holes come and how they grow and become larger. So this is something that's very new and developing, but yeah, keep your eye on it. I'll quickly end by previewing like a Cycle 2 program that I'm leading that I'll be spending most of this coming year working on. And it really has to do with this question of trying to find these very metal-poor and metal-free stars. So one of the holy grails of cosmology for the longest time has been to find the first generations of stars, POP3 stars that do not have any metals in them. And so while directly seeing these stars forming at very high redshift would require you to put a telescope on the moon and push to like 40 Earth magnitude, what we can do instead is we can look at slightly lower redshifts, redshift 6, 7, 8, 9, and still see pristine gas giving rise to essentially metal-free stars. And so excitingly, we already see some hints of this. So there are some objects that we spectroscopically see have these very metal-poor pockets embedded in larger galaxies. And so the idea is if we use the power of gravitational lensing, we could push even lower and get to limits that are very competitive with the kinds of things that we are doing with halo stars in the Milky Way and directly see these halo stars forming in situ at higher redshifts. And so that's what our program is hoping to do. We have 47 hours on like one of the most powerful gravitational lensing clusters. And so stay tuned for us trying to push and find some of these first generations of stars ever. But yeah, that's my summary. Thank you so much for listening and happy to take questions.
We have time for one question and then comes. Think of the hand up.
That's an annoying little question. How many of those little red dots are M dwarfs?
How many of our little red dots are M dwarfs? The answer is 0, right? Because we get spectra for every single object in the field of view, right? So that's the beauty of the GRISM spectroscopy work. So you have the photometry, but every object has spectra. So no M dwarfs. But if you're selecting them purely photometrically, indeed, It turns out that M dwarfs are also little red dots, but not the kind that we're talking about.
We
Okay,
fixed the color selection. We get fewer dwarfs now we know.
let's thank Rohan again. Okay, our next speaker is going to be Wren, who's going to talk about quiescent massive galaxies and cosmic groups.
Yeah, awesome. Thank you for the introduction, and thanks to everybody for still being here and all the organizers and all the leads. This is my first year as a Hubble Fellow at Stanford, so it's been so fun to be here and see just the amazing diversity of science that everybody's doing. So I am an observer. I look at very distant galaxies. And so the thing that I've been most excited about over the last year and a couple months is these new observations that we've been taking with JWST. So I said I was going to talk about quiescent galaxies. I'm really going to zoom way out and say why I am so excited about JWST data as somebody who likes galaxies, and then attempt to show you as many pictures that will hopefully show up okay on the screen as I possibly can. So this is work that's been done in collaboration with so many amazing people. It's really been a long year, and we've been bogged down with lots of data reduction, with new things that we don't understand. And like Rohan was saying, it really takes a village. So I'm very thankful for all my wonderful collaborators across many different teams that have been helping to get these results through. So I wanted to start by kind of reframing the fundamental problem that we have when we're trying to figure out what's going on with distant galaxies. And it's that we really care about the physical properties of galaxies. We care about their stellar masses and ages, how rapidly they're forming stars, all of these types of things. But as with almost all of the rest of you, our fundamental problem is that we only observe light. And so we have to have these complex models that are able to translate the light that we see back into these physical properties. And so in my subfield, the way that we typically do this, you can use GRISM or spectroscopy, though those tend to produce smaller samples than imaging still. So for the sake of this talk, what we tend to do is to take images at many different wavelengths. So this is an example of a local galaxy as seen all the way from 200 to 1800 nanometers with the Hubble Space Telescope. And then what we do generally is we sum up all the light. We put some big aperture around the entire galaxy, and then we reduce all of these beautiful 2D images with all of this complex structure into a single plot. This is a spectral energy distribution, so in flux density as a function of wavelength. So each image gets turned into a single data point. And once we have this, we can fit these complex stellar population models to these data points. And these models this is what I spend a lot of my time doing, is building and refining these models. They have so many moving parts. It's not just redshift and stellar mass. You know, Karthik was telling us yesterday about star formation histories. There are also assumptions about dust. Often we're fitting a dozen or maybe even 20, 30 free parameters in these models that have really been calibrated at low redshift, and we don't understand exactly what shouldn't translate to high redshift yet because we haven't had the data. And so the point that I wanted to make here is that because this is the way that we're inferring almost everything we know about the physics of distant galaxies, is that anytime you can improve how you put data in this plot, so anytime you can get deeper or higher resolution or cover new parts of wavelength space, it can really dramatically change these models and how you're inferring these physical properties. And it can really change everything you think you know about how the universe is changing over time. And so that fundamentally is why I'm so excited about JWST, because it is the first view that we're getting into the resolved faint infrared universe. And I cannot believe that it's the last day and nobody has shown a GIF yet of how amazing JWST is. It's probably because everybody showed them last year and I wasn't a Hubble Fellow yet. But this is going to go from data from the WISE satellite, which was basically our best view before of these kind of 3-ish micron wavelengths, to the very first image that probably all of you, unless you were on the commissioning team, saw from JWST. So you can see this star resolved down into this tiny point source with these big diffraction spikes that are extremely annoying to deal with. You can see all of these things that were kind of big blobs in the WISE data. Hopefully you can see they resolve down into these tiny galaxies. You can start looking at the morphology of these distant objects. And then of course, there's all these faint sources that pop up above the sky. And so this really is a whole new era in how we're able to look at galaxies in the distant universe because we're able to probe this infrared emission just so amazingly. And so, one of the things that I wanted to sort of focus on for this talk is to come back to this idea of, how are we doing these analyses most commonly? And the point I want to make is that galaxies are not points. You probably shouldn't just sum up all the flux and look at, one model to fit the entire galaxy, especially not once you have this amazing high resolution data. And so the first kind of way I want to talk about this is by saying that properties like, for example, the size of a galaxy, you can see here, this galaxy is really big over here, and then it gets smaller and smaller. And then I don't know if you can even see the emission over here, but it's a tiny offset clump. So properties like size, like star formation rate, like dust, all this stuff depends on wavelength, because different wavelengths are really fundamentally probing different physical bits of the galaxy. And so over there, you're really tracing the rest frame UV, which is showing you the most unobscured active sites of star formation in the galaxy. And it's not until you get to the rest frame near IR that you're really starting to get those older or more obscured stellar populations, and you're able to trace the actual stellar mass profile of the galaxy. And I bring this up because this is what we had with Hubble when we were trying to look at the peak epoch of star formation in the entire universe. We were always seeing the rest frame UV, or maybe if we were lucky, the rest frame optical at cosmic noon. And so we didn't have a good sense of even, I would argue, the total stellar masses of galaxies, but certainly not things like sizes. And so it's really exciting that we can now start to probe these infrared distributions of the stellar light of galaxies, even at these redshifts that aren't maybe as flashy as the redshift 10 results, but I would argue there's a lot of really interesting stuff to be done because we're seeing this infrared emission. And so this is the first thing that I really wanted to do as soon as we got data from JWST, is just a probe of how much does this matter? And so this plot is showing the ratio of the sizes of galaxies at 4 microns, which is the longest wavelength that we have on JWST NIRCam, to the size at 1.5 micron, which was the longest wavelength that we had with the C3 on Hubble. Oh gosh, I'm talking slowly. Okay. So anyways, there's a scatter plot. I'll skip past it. But basically, galaxies are smaller at redder wavelengths. It's about a 30% effect. So galaxies are much smaller than they look to be with Hubble. So we probably got our previous view of galaxy growth was actually quite biased because we were looking at these bluer wavelengths that weren't actually tracing how stellar mass was assembling over time. As part of this work, this initial study, we didn't have very many of these massive old quiescent galaxies that we got a great intro to yesterday from Ariana. And so in the JADE survey, I was taking advantage of this really deep data that we have to start looking more at these quiescent things. And we got really sidetracked by something that I was not expecting to see, but really should have been expecting to see. So these are examples of 3 of these massive quiescent galaxies at about redshift 1-ish, as seen by, again, the reddest wavelength on board JWST. These are well-studied, well-known, people have been looking at them for a decade. And now I'm going to show you how they look in JWST, not at a redder wavelength, but actually at the same wavelength, with the key difference here being that JWST has a giant mirror, and so it has 3 times the spatial resolution. These images are also a little bit deeper. And hopefully you can see there's all these little blobs in these images that we didn't see before. And so when we actually run an analysis and try and figure out what redshift all of these little tiny sources are at, everything that I've circled here in green is at the same photometric redshift as that primary galaxy. And this is really exciting because what we're seeing are satellite galaxies at redshift 1 and even actually all the way up to redshift 3. And this is really cool because people looked at this before with HST because this is what we think causes most of the evolution and the size of quiescent galaxies, is that they basically eat all these little companions and then poof up. But they were only able to look where they thought they were complete at stellar mass ratios of 1 to 10. which is almost exactly the same as we heard from Ekta, is like, that is enough to really mess up your galaxy and is not, it's really the tip of the iceberg of the satellite population. And so now with these JWST imaging, we're actually able to see all of these tiny companions. This is not a mass complete plot, but this is everything that we found that we think is a satellite, all the way down to stellar mass ratios of things that are, 10 to the 5 times fainter than their host. So this is really cool because it's opening up some new studies of really understanding the demographics of the satellite population and how this is evolving all the way from when the universe was well less than half its current age to now. And then the second thing I wanted to talk about this, galaxies aren't quite particles thing, is that I'm very excited to move beyond an era where we're primarily just putting the entire integrated flux of the galaxy on this plot and fitting a single model, and move to an actually approach where we're mapping out the properties of these galaxies. And so that looks something like this, where instead we're breaking the galaxy into many different parts and we're fitting a model to each individual part of the galaxy. And it turns out that the ideal data set to do this is to take advantage of what I think is one of the other most innovative features on board JWST, which is this huge suite of medium band filters. So there's 2 or 3 medium band filters for most of the broadband filters on board JWST, which allow you to really highly sample your galaxy's spectral energy distribution. So it looks something like this. So again, the gray is a model of a galaxy, and the blue is basically what most JWST surveys are actually observing for these things. And you can imagine wiggling this model and it's still basically fitting the data quite well. And this is what happens if you add in all of the medium band filters as well. So you really pin down, the location of these strong emission line features, the breaks, and you can start to really constrain the physics of these galaxies. And if you run some numbers, it improves our estimates of the properties by a factor of about 3. And you can also use this to probe strong emission lines and really map them by using the difference between the medium band flux and then the broadband flux that it lies in. This is about what this looks like. This is from the GEMS survey, which is led by my close collaborator, Christina Williams, where here all of the green emission is actually strong line emission, all the way from the 3 micron pod line at low redshift up at the top down to Paget alpha, H alpha, H beta, and O3. And so the thing that I'm extremely excited about in about a month is that we'll be observing all dozen of these medium bands across this full uncover field that Seiji introduced yesterday, which is great because I don't have any time left really to talk about it. But this is a survey involving many wonderful people of the Able 2744 lensing field, which already has all this broadband imaging. It's actually the same place that Rohan was talking about his GRISM program. That's going to happen in this field. We have spectra. We have all kinds of data. So it's becoming one of the best calibration fields for JWST. And so we're about to add all dozen of the medium band filters across this full pointing. So something like 50,000 galaxies. And we'll be able to use this really high spatial resolution to map out these emission lines, which aren't really showing up, but there's some really weird elongated galaxies that we'll be able to use to really probe this emission at, in some cases, sub-kiloparsec scales at very high redshift. So thanks. I will leave my conclusions here and take questions. Thank you.
Thanks, Ron. That was really cool. I have a very quick question, which was for the galaxies you're finding satellites around. What's the range of the number of satellites you're finding from them? So the groups with the same photos.
Yeah, so we have a plot of the number of satellites per host in the paper. I just didn't want to show it, but it's something like between 2 and 15. Yeah.
Getting the field you just mentioned, is there any multivariate coverage in that field? Was it chosen, I guess, where the deepest X-ray images are or anything like it? Or?
Yeah, so it's one of the Hubble frontier fields. So it was chosen mostly because the field, I'll just show this again because it's pretty. So actually you can see here. So there's the really bright star, and then everything that's kind of white in this image is the cluster. And so it actually turns out this is two merging clusters. And so this is the largest area with a magnification greater than 2. So that's why we chose it. We have really been struggling with the lack of HST coverage, which is actually very important at low redshift if you want to constrain things. So as part of the medium band program, we're getting on JW 070 and 090, which should help a lot with the multi-wavelength coverage. And there's Chandra too. So this is where that redshift 10 X-ray source is.
Okay.